Question number 4. Question number 4. Question number 4. Share. Question number 4 says, state whether the following combinations will make a buffer. So here's the first step in buffers, and that's what chapter 15 is all about two things, buffers and acid-base titrations, where buffers are created. Okay, so buffers and acid-base titrations are basically the two concepts we have to accomplish in chapter 15. Okay, so today our focus is recognizing buffers and maybe plugging and chugging into the HH equation to find its H plus. And then it's pH. All right, first things first. The straw and beaker. And inside that beaker, we're going to write what we have if I mix those two things together and make one beaker solution. I have those three things floating around in my beaker. Now, the NH4Cl is called ammonium chloride. And it's a salt that's soluble. It's going to break up completely. And that's why I have those two guys written separately, yes? All right, so Austin, which one's a total spectator? Thank you, the CO minus, the one that's going to be neutral. We're just going to kick into the curve. And so now the question is, are these two ions conjugates of each other? Okay, Kelsey says yes. How do you know they are? One has an extra hydrogen, the other doesn't. And that's how you recognize conjugates of each other. NH3 doesn't have the hydrogen. NH4 plus 1 has the hydrogen. Can it be more than one hydrogen difference? No. Can it be strong stuff? No. It's weak. It's weak stuff. Okay, so this constitutes a buffer. Now, here's a new piece to the puzzle. If I tell you that the Kb of NH3 is 1.8 times 10 to the minus 5, and I tell you that his counterpart, his conjugate, his kissing cousins, Ka, is 5.6 times 10 to the minus 11, minus 10, who's better at dissociating in water, Jordan? The NH3 is a better dissociator in water, and how did you know that? Because the exponent on the Kb is a bigger value than the exponent on the Ka. Would everybody agree with that statement? A minus 5 is a bigger number when it comes to math than a minus 10. Yes? So the base is better than his conjugate acid. Agree? So therefore, the buffer that's made anytime between ammonia and ammonium ion is going to be a basic buffer. That means the pH is going to lie above 7. pH is going to be somewhere above 7 because the Kb is better than the Ka. You need to know that. Absolutely yes. You've got to know that. Absolutely yes. Okay? So we're doing it in 4. We're learning how to recognize buffers in question number 4. Okay, so that was A. A, first things first, show me what's floating around the beaker. Cross out anything that's neutral or a spectator. Okay, and then analyze. Do these two guys differ by only an H? Yes. Therefore, this is a buffer. And that's the conjugate acid-base pair. I have to give you these values in order for you to know whether it's a basic buffer or an acidic buffer. If you don't have a Ka or a Kb value, you wouldn't know that part of the buffer piece. Yes?
So if the non-spectators differ by
If the non-spectators differ by 1 H, it's a buffer. Okay? Can't differ by 2 H's or 3 H's. 1 H only. Or anything else. Yes? All right, is everybody with me so far? Next one. All right, the next one is HClO and KClO. So let's draw our beaker. We have HClO, just a plain old weak acid. We have K plus, and we have ClO minus. So, Mariah, who gets kicked to the curb? Who's spectating? The potassium. Okay. Abby, do those two things differ by an H? They do. Therefore, this is a buffer. So now what we need, and I have my book open. Now we need a Ka or a Kb value, and all we really need are exponents. So I'm going to go find, I moved my page earlier. I don't want the glossary. There we go. Okay, so ClO, 3.5%. All right, the Ka of HClO is 3.5 times 10 to the minus 8. Okay, Kb of ClO minus then is going to be something about 10 to the minus 6 or 7. Can you agree with that statement? Without me putting anything here, can you agree with that statement? Got to get to the point where you can do that without a calculator. Now, how can I do that? Because we know that the Ka times the Kb must equal Kw, which means 10 to the negative 8 times something gives me 10 to the negative 14. What does that something have to be exponent-wise? I'm going to think a negative 6. It might be a negative 7 just because of this extra stuff here, but I'm going to think negative 6. All right, so who's better, the Ka or the Kb? The Kb is better, so since the Kb is bigger than the Ka, the pH is going to be above 7. Agreed? So we have a basic buffer then, as long as I'm given that extra piece of information, we have a basic buffer anytime HClO, hypochlorous acid, and hypochlorite ion, ClO minus, are floating around in the same beaker. It is a buffer. It is a basic buffer. Yes?
For those questions like this where it just asks, like if they teach the buffer, is this all necessary to do, or do you just do like the initial part of it?
You could just do the initial part, but you're eventually going to have to know when you are given either a Ka or a Kb, whether your buffer is acidic or basic. Because sometimes it might say pick the best pair out of the following that will give you a basic buffer. So you got to know how to do that part too. But yes, you're right. I really don't have to go any farther than this just to say yes, it's a buffer.
Oh, I was just wondering.
I'm going a little bit deeper with you. Okay? Any questions? Other questions? So far? Buffers are not hard. They're just a little different. All right, the next one. This is what we have in our beaker. We have K plus and CO3 minus 2, and we have H2CO3. All right, so the question is, who's the complete total 100% iris spectator? Potassium is. All right, Matt, do I have a buffer? No, I don't have a buffer. I don't have a buffer, Matt. Why? There's more than one H difference. Can't be 2, can't be 3, can only be 1 for them to be a buffer. Okay, so this is not a buffer. Not a buffer. They each would end up doing a dissociation equation all on their own. And since they're not conjugates, they don't make a buffer. All right? The next one, the next beaker is Na plus with HSO3 minus and Li plus with SO3 with SO3 minus 2, and that's a minus 1. Yep. All right, who are my complete and irate spectators?
Sodium.
Because they are my neutral ions, yes? All right, so now, Hayden, the question is, are those two guys are those two guys conjugates of each other? They are. So this is a buffer. So I either have to have the Ka of him or the Kb of him. Now, you might say, wait a minute, Ms. Madney, that's not one of my ions. That is acidic. I know that. But he's amphiprotic, which means he can be either. So in this case, he's going to have to act like the acid, agreed? Going to have to act like the acid. So he has a value of, it says he has a value of 1.0 times 10 to the minus 7. What it says he has. So if the Ka of HSO3 minus is 1 times 10 to the minus 7, what would the Kb of SO3 minus 2 have to be? Same exact thing, because H plus times OH minus yields, well, that's true. H plus times OH minus, or Ka times Kb always equals what? Kw, 1 times 10 to the minus 14. Do we know that H plus times OH minus also equals that? Okay, just making sure. All right, so therefore, what kind of buffer do I have here? Neutral. That's not often found, but in this particular case, we have a neutral buffer. All right, so we have one more to do. The one more to do is NaCN and HF. Na plus, Cn minus, and HF. All right, so Stephanie, who totally spectates in that beaker? Na. Question is, Janae, is that a buffer? They're not even related. Cn minus, cyanide ion, NHF. One's a weak acid and one's a weak base, but they're not related at all, right? So this is no buffer. No buffer. Okay? You with me so far? Okay. So let's look at one more question. Maybe two more, but one more question. Let's look at question number 5 and see if you and I can do a little plug and chug into what we call Mrs. Matthew's HH. Not the book's HH, that's called the Henderson Hasselbalch, and that doesn't look very pretty if you've seen it yet. We're going to see, can we take a 100 milliliter solution that has 0.3 moles of HF in it and 0.2 moles of NaF in it, and find the pH when we know what the Ka is. The Ka is 6.9 times 10 to the minus 4. Can we find H plus and then thus the pH? Okay, so let's see if we can do that. So let's take away all that other stuff and let's bring this down just a little bit. You have this on a piece of paper, yes? You're working this on a piece of paper, yes? Question number 5. Matthew, on a piece of paper, yes? So we're going to do a buffer. Let me draw you the picture first. The picture first is we have HF and we have NaF and the Na spectates, yes? Okay, and we're told that we have 100 milliliters, and in that 100 milliliters is 0.3 moles of the weak acid and 0.2 moles of his conjugate base. I know there's Na plus as well, but we don't worry about the Na plus. We're told that the Ka is this. Now, what is Mrs. Matney's HH? It's an equation that we've got to have, and if we don't remember it, what we do is we go to the dissociation of the acid in water, makes F minus and H3O plus, and so the expression from that is HF, excuse me, it's not HF, it's F minus and H3O plus. It's F minus and H3O plus on the top. And it is HF on the bottom. Do you already know how to do that? Yes, I do, Ms. Matney. Do you already know how to write the expression from that? Yes, I do, Ms. Matney. Now, out of all of these 4 pieces here, we have the F minus concentration, 0.2 over 0.1. We have the HF concentration, 0.3 over 0.1. And we have the Ka value. What's the only thing missing? Well, yeah, I could go find the Kb. Good. Out of this expression, I have the Ka, I have the F minus, I have the HF. What's missing? Can you find it if he's the only thing missing? Yes, you can mathematically. And so what has happened is Ms. Matney's HH is not this, but it's this rearranged to solve for H3O plus. It looks like this, Ka times HF over F minus is my H3O plus, which I'm just going to write as H plus. Now, do I have to rearrange it? I don't have to, but it does make your life a little easier with some buffer questions to rearrange it. But it really is just your Ka expression rearranged. That's what we call Ms. Matney's HH. And when NIMSY came into our schools, guess what they taught? They stole my idea. No, they didn't steal my idea. They just were trying to find easier ways for AP Chem students across the whole nation to understand buffers better. It made me feel good, because I'd already done that a long time ago. They did not steal my idea. They were other AP Chem teachers wanting to make sure that this stuff that tends to be hard is understood. So it's just this expression rearranged. So all I have to do is, let's go up here. Let's do 6.9 times 10 to the minus 4 is my Ka. I'm going to show you what this looks like. My acid's on the top, that many moles, sitting in 0.1 liter. The base is on the bottom, that many moles, sitting in 1 liter. What happens to the liters? They end up canceling out. They end up crossing out of each other. That's why you'll see the Henderson-Hasselbalch equation rearranged to say Ka times moles of acid over moles of base. How do you remember the acid's on the top and the base is on the bottom? Alphabetical. Ka times A over B. Since you got an A here, you put the A on top and the B on the bottom. And since it's Ka, it will always equal H plus. Yes? Okay? So basically what this turns into is about 10.5 or 10.4, 10.45 maybe, 10.45 times 10 to the minus 4 is equal to my H plus when I go and do my math. And then I minus log it to get my pH. Okay? All right, we're going to go back to percent composition, but I want to see. That's going a little deeper, a little extra. Here's a little extra ticket. What we're going to do is I'm going to see, can you tell me yes or no? Or are these buffers? Okay? Now, I'm going to warn you. Anything that's strong, if you need to draw a little thing, you don't have to. You just tell me yes or no. And then what I have asked you to do is, if you tell me yes, tell me what the conjugate acid, conjugate base pair happens to be. Okay? You may write directly on this little sheet, so I don't even have to do that. And then we'll go back and make sure we know what percent dissociation is. We don't want to go any farther than that today on buffers. You can write directly on this. This is just telling me whether they are or not. If you need to write on the back, if you need a little more space, or if you need to use a how-to paper, you just have to get to the point where we can recognize what a buffer is. We're going to be able to recognize what a buffer is. Huh? Yeah, you can do it directly on this little piece of paper. If you need more paper, I'll give you a half sheet if you feel like you need more. telling me yes or no, and then if it is a yes, you're telling me what the acid base conjugate pair happens to be. Just like we did with our beakers before. We have got one beaker left up here from number 5 that we have HF and NaF. So we have HF, Na plus, and F minus. I crossed out my Na, and then what I have left is how I decide whether it is a yes, but you tell me yes or no first. Is it a buffer or not?
I circled the entire.
Okay, cool. Yes. The conjugate acid base pair, like the one we have up here is HF and F minus. They're going to be close to the acid conjugate. After you say yes, if you tell me yes, he's a buffer, then tell me what the conjugate acid base pair is. That one's conjugate acid base pair is HF and F minus. I just want to tell you.
I think you put two longer on next to each other.
That you missed. Just trying to say, this is for you. It's not so much. I'm going to see what you're getting from this, what you're gleaning from this. This is not for grade. This is just for me to kind of get an idea.